Good morning everyone. Today we will start with the actual filter designing stuffs. So, among the different filters, you have FIR filter, okay, which are regarded as finite impulse response filters. So, in the FIR filters, as I previously told you, as the name suggests, finite impulse response filters. So, what we have over here, basically, when you give an impulse to a system, so when we give xn, we get yn, right? So, however, when we get delta n, we get hn. Now, this hn, it is basically the characteristics of the system, okay? But in place of xn, when we give delta n, we again get this hn, right? Now, when we get this hn, so there are two possibilities. This hn, it can be an infinite series, and it can be finite series. Finite series means the hn series, it will be time limited. Okay, so it is time limited. That means within a particular, after a particular period of time, after that there will be no response. No response means zero amplitude values you will be getting. Whereas in the infinite series, you will find that this hn values, we are getting the values from the system even at time tending to the infinity. However, as the time progresses, the stable systems, they have amplitudes which are tending to zero. Okay, not completely zero, but tending to zero. At time tending to infinity, we will be having amplitude values which are tending to zero. Okay, so the systems that have hn values which are infinite in series, they are regarded as IIR filter, infinite impulse response filter, whereas the systems which have finite series of hn, they are regarded as FIR filter. Okay. Now, if you look in many of the textbooks, you will find that they start the filter designing aspects using the IIR filter. Okay. However, uh, my way of teaching is slightly different. I start with the FIR filter. The reason being, making you understand the concepts of filter designing. As per me, it is easier in the FIR filter than in the IIR filter, because FIR filters can be easily designed. So once we get you people can get a grasp of the what are the easy stuffs, how to design the FIR filters, and then when we go towards the more complex sums, you build up a base and then you are moving towards the complex numericals. So that is the main funda with my teaching. Okay. Now, when we call the digital filters, they will be taking the digital signals. Okay. Now, over here, if you see the digital filters, they are being represented with transfer function hz. And what is hz? What is hz? That is the important thing. Okay. So before coming to the hz, let us take the example of non-inverting amplifier. Okay. So I hope everyone knows what is a non-inverting amplifier, even the biotech people, right? So this is a non-inverting amplifier. So we give V in, we get V out, and we are having 1 plus R2 by R1 as the output. Okay, multiplied by Vi. Now, if you calculate, if you take this Vi and bring it onto the left hand side, we get a component which is basically V0 by Vi, and it is nothing but the gain of the system. Okay. Now this is equal to 1 plus R2 by R1. Right. Now the thing is that in all of this, if you see in the whole of the circuit, we are having all the real components. We do not have any components like capacitor or inductors which can induce the frequency dependent component over here. Okay, that's why if you see the gain over here, it is frequency independent. It is frequency independent, right? Now, suppose in place of R2 or in some combination, whether series or parallel combination of the R2, I place a capacitor or an inductor, or it may also be in the case of this R1, if I place some capacitor or inductor, whatever combinations you can think of. So when I will be doing that, what I will be doing? I will be introducing a frequency dependent character into the system. Then this gain, it will be converted to A omega. It would be a function of A omega. Why this omega? Because I am talking about this non-inverting filter, and non-inverting filter, it is in the it is working in the continuous time domain, and we already talked that when we are talking about both digital filter and the analog filter or the continuous time frequencies, we will be using this omega as the analog or the continuous time frequency representation. Okay, so this parameter a of omega, it becomes this thing. Now if this becomes this thing, then V0 will also be a function of the frequency, Vi will also be the function of frequency. Okay, so we get A omega equals to V omega, V0 omega divided by Vi omega. Now if you see over here, what is Hz? Hz is again Z. Yesterday only we have discussed, it is equal to e to the power j omega t, right? So again it is a function of the omega. So Hz, it is equal to Yz by the Hz. What is Yz? Y is always associated with, conventionally it is associated with the output of a system. See, you are having the output of the system, and Hz, it is associated with the input of the system. See, over here it is also the input of the system. It is the simplest method to remember what is Hz, because in many cases you will find, even when I was a student, or and even when I was starting to teach, I always had this confusion: what is Hz? Whether it is Yz by Xz or Xz by Yz. It happens, right? It's a human nature. So when you are starting, this thing will be there in your mind. But if you remember this analogy, that A equals to V0 by V in, which you have already studied in long back in your UG classes, then it will be easier for you to get this thing in mind for a longer period of time. Okay. So once you have this, so you see we have got the transfer function of the system, which is equal to Yz by X. Okay. Now coming to the Fir filter, they are also regarded as non-recursive filters. Okay, whereas IIR filters, they are regarded as the recursive filters. Non-recursive filters and recursive filters. Now, what is this? So, when you see this example over here, where we are having having the real component, okay, so all the real components, and we'll be having the real values, that's okay. But if you see, there is a feedback loop. Okay, so this feedback loop, if you see, you are having V in over here, by virtue of the virtual ground or this virtualness of this op amp, both the terminals they try to be at the yeah, both inverting and non-inverting terminals of an op amp tries to be yeah, this is the basic characteristics of an op amp. Mm-hmm. Hmm. Both the terminals of an op amp tries to be at the same potential. If there is a ground, then the other one also becomes a ground. But over here we are having Vi, okay, because no current is flowing through. If no current is flowing through, the whole drop will be across over here also. So at the input, this non-inverting terminal will be having Vi, and over here also we are having Vi. Okay. Now, if you see, we are taking this V0 and then again with the input, the present output, it is also getting involved to get the fresh output. Okay. So it may so happen when you are applying this frequency dependent components, say for example the capacitors and the inductors, you may be having some information not only from the present output but also from the past outputs. So we are taking the feedback information from the present and the past outputs to calculate the present output of the system. So those kind of systems, they are regarded as the recursive filters. Okay, they are regarded as the recursive filters. On the other hand, if you see the FIR filters, they are non-recursive filters. That means they will not be having any feedback loop. They will not be having any feedback loop. Okay. So, is there any advantage? Is there any advantage for that? Okay. Yes, there is an advantage. What is the advantage? The advantage is Hz is equal to summation of I equals to 0 to n hi z to the minus I equals to h0 plus h1 z inverse plus h2 z to the minus 2 plus hn. Whereas if you look into the higher filter, the equation is somewhat complex. So since the feedback values, present and the past values, they are not used for the computation of the present values, our implementation equation of the FIR filters, they become very easy, okay, as compared to the FIR filter. Now if you see over here, it's just a simple equation. So what will be the this thing? If you have some hn, some values, say 1 3 5 7 8, say this thing, you just perform the z transform, there you go, you are ready with the filter. It's very easy, right? Now from here, can you tell me where would be the poles and the zeros of the system? First tell me the where would be the zeros of the system, sorry, poles of the system, because there is no denominator component. But our criteria is we should have poles. So where would be the poles? This is a clear indication you don't go and study. Yeah, Anjo. You didn't say, na? Anyway, so if you see over here, we are taking an example. We are taking a very simple example. Z is equal to 1 plus 4z inverse plus 4z to the minus 2. So if you want, you can break it down into this, yeah, a plus b whole square. Just a simple formula. You have been, done it. Okay. You have put it over here like this. Then numerator and denominator, they should be divided with the highest power of the order of the filter, minus of highest power of the filter. So if you see, we get this one and this numerator, this one. So we get z plus 2 multiplied by z plus 2 divided by z square. See, still now it is just very basic mathematics. Class 10, 11, 9, 10, 11 mathematics. And I have not got into any integration nor any differentiation, nothing. It's very simple mathematics till now. Okay. So what is happening? Now from here we have to, from this equation where we are having the z components, we have to find out the poles and the zeros. If we are having z inverse terms, delay terms, then that transfer function is suitable for the realization of the filter. I am telling you time and again, that equation is suitable for the realization of the filter. However, for finding out the poles and the zeros, you have to convert the equation to these z terms. Okay. Now if you see, the denominator, it has become z square. Now z square means there will be two poles at the origin. Okay, two poles will be at the origin. If you try to generalize, this is just a second order filter. If you want to generalize this thing, you will be getting zn equals to 0. So if you put it in this equation, this if you try to find out the solution for this one, so again you will be getting divided by z to the power n, right? So z to the power n is 0. So you will be having n number of zeros at the origin. Okay, you will be having n number of zeros at the origin. So that is what, if you see, we are having all the poles at the origin. This is a very good question. Many people may ask me in the interview also. In FIR filters, where are the poles? Many students, they fail to answer this thing when they come for the PhD interview or even in the comprehensive viva. So the poles of a FIR filter, they are always located at the origin. Okay, they are always located at the origin. Now what does that tell us? Go back to my previous classes and can you tell me, if all the holes are at the origin, so what should be the outcome? अरे खाना नहीं खिलाया अभी, तो केला भी देते हैं ना सुबह दूध के साथ. हाँ, no, that may be one game, but if it is only single pole, it may be a single pole, no? Zeros are different. If you see, if you find out the zeros, are here. So cancel कहाँ से हो? Pole over a pole, they increases their efficacy. लेकिन if you see, they will not increase the efficacy. The reason being, the nature would be same. If you see the radius, it is same at all the frequencies. So in a FIR filter, pole will not be able to help you out in what you call, in creating some filter responses. It will be very difficult. because to each of the frequencies the radius is 1. And we discussed in our last class that to modulate the frequency response, we need to place the pole nearer to the frequency axis so that they can have an we can create a specific frequency response. So that is now out of question. So that is why one important thing is that is why in FIR filters the placement of the zeros, they regulate what should be the frequency response of the filter. Okay, one is that. So but that is much more advanced stuff. उससे भी basic preliminary एक ये बोला था while discussing about the comparing the this analog and the digital filters. जाके कॉपी खोलते भी नहीं हो घर में जाके खोलते हो? Yes, not more stable. FIR filters will be inherently stable. वो हमेशा stable ही रहेगा because all the poles they are within the unit circle. There is no way that you can place it anywhere else. So FIR filters they are inherently stable filters because of this reason, because all the poles they are present at origin. वो वहां से वो move ही नहीं कर सकता. Okay. So that's why see मैंने यहाँ पे लिख के भी दिखाया, they are inherently stable, right? So हाँ ये जो मैंने बोला Z inverse they represent the delay and you will be having the realization. Now coming to the IR filter over here, Hz, its generic equation it is given by summation of I equals to 0 to n ai z to the power minus I divided by 1 minus summation of I equals to 1 to n bi z to the power I, which is equal to something like this. So this is a polynomial, say pz, this is qz, this is another polynomial. Now let us take an example. So over here, so I am having this hz which is equals to 1 plus 4z inverse plus 4z to the power minus 2. Okay. Now hz, just a few moments back I told you I can write it like this. Yz by xz is equal to 1 plus 4z inverse plus 4z to the power minus 2. Now I will take this x over here, so I get yz equals to xz plus 4z inverse xz plus 4z to the power minus 2 xz. Okay. Now if I perform inverse z transform over here, I will get yn, which is the output of the system, is equal to xn plus 4 of x of n minus 1 plus 4 of x of n minus 2. Okay. In this equation, these are the delay components, right? Now let us realize the filter. What is the what do you mean by the realization filter? We have got some equation, but there should be some algorithm or there should be some process how the signals will be transferred through that algorithm so that you get the output. Okay. So that creation of that algorithm, it is regarded as the realization of the filter. So over here, this diagram, this is the realized filter of this equation hz equals to 1 4 z inverse plus 4 z to the power minus 2. If you remember the operators of the digital filters, we only have z to the power minus 1. We do not have z to the power minus 2 or z to the power minus 3. So this z to the power minus 2, z to the power minus 3, they need to be recovered from z to the power minus 1. from the delay function. So let us take, so for the realization of the filter, we know that when we are talking about a system, we are giving an input, we are getting an output. So if it is in the Z domain, we exit and YZ, right? Now I have initially exit YZ. I have put two numbers. Okay. So if you see YZ equals to XZ plus, so YZ we are getting over here. So we have got an adder. So directly the XZ will come over here, and then it will be added with the other two components. What is the second component? There is a Z inverse delay. What is getting delayed? XZ is getting delayed. So from the XZ there will be a branching. This delay I have got. Okay. So this delay, after this delay, this is getting multiplied with 4. So we have a multiplier operator which is getting multiplied by 4. Then we are having adder. So we are having added over here, and it is going to YZ because it is being added to here. So up to this one we have completed. Now the next part, we have Z to the power minus 2. Now in the Z to the power minus 1 we are already implemented. So in series, if you put another Z inverse, then combination of these two is Z to the power minus 2. Then again it is from the branching of the exit, so this has been taken care of. Then there is a multiplier of 4. This multiplier of 4 is here. Then it goes to the adder over here. This one. So this is the realized filter of this one. अरे आपका चार्जर कहाँ है? बैटरी मोड में. Okay. The next thing is that let's see what happens whether this system is working fine or not. Okay. We know that if we give delta n, that is the impulse input, then what should be the output we should be getting? As per this equation, we should be getting of an output of Hn is equal to 144, right? We should be getting this output. Why? This is the impulse response of the system. This is the impulse response of the system. Okay, which will govern the transfer function of the system. The Hn and Hz, they are the same. Now let's see whether it is the same or not. So let us create some nodes in the realized filter. We are having A, B, C and D. D is nothing but the YZ. So A is this point, B is this point, C is this point. So let us see the thing. When n is equal to 0, A, it is getting a value of 1, right? What will be the value at B? Previous instance, nothing. B is 0. Okay. Again C, इसका 2 इंस्टेंस पहले, again 0. Sorry, no, this one. So B 0, this one 0. So we are having at this node 1 plus 0 multiplied by 4, 0 plus 0 multiplied by 4, 0, 1. So output is 1. Okay. Next what? The next instance over here, let me change the color. It is 0. So at A point it is 0, but the previous instance it is 1. So at B we will be having 1. उससे एक और इंस्टेंस पहले C it is 0. Now we are having in the second instance 0 plus 1 multiplied by 4 plus 0 equals to 4. This is the second instance. What happens in the third instance? We are here. Again, let me change the color. 0 at A. Okay. At B, 0. At C, 1. 1 multiplied by 4. So, ये आ गया 0 plus 4 equals to 4. Okay. So, after that again if you do it, zero at A, B में 0, C में 0, right? So thereafter it will be 0 0 0 0 0. Okay. So from here if you see XZ, again we get the same thing. So our HN is 1 plus 4, 1 comma 4 comma 4. Okay. So is this matching with this one? Yes, definitely yes. So this is called the direct form of the realization. When you show over here this one, this is called the direct form of the realization of the filter. Okay. Similar to this one, there is another component which is regarded as the signal flow graph. It is basically the same, just the notations are something like this. These adders, they are being replaced with the nodes, and the multipliers, they are replaced with this add. Okay. Any doubt? No. Good. Now again, the same filter, it can be represented with this way. Initially I showed you over here the same thing. Okay. So 1 plus 2 z inverse, 1 plus 2 z inverse by z, ये इसको ये करोगे, then this is a subsystem, this is a subsystem. ये एक system A है और system 1 you can say, and this is system 2. So let us design the system 1. See x dash ये चला गया y z में, z inverse 2 इसमें आ गया. Similarly we are having another subsystem 2 over here. We are just joining it. So this is called cascade type of realization. When you are having multiplication in between, it is called cascade type of realization. Okay. यहाँ पे एक ये गलत है. So this should be 2. Okay. So this is called cascading. And this kind of filters, they are Bibo stable. That is, all the poles within the unit circle, they are stable in, since they are within the unit circle, these filters, they are inherently stable. Okay. So from the next class I will start with the FIR filter designing. So I have shown you how to calculate this impulse response. So for the first filter and for this second filter, or second not filter, the realization, both are the same filter. But the second in the second realization, you find out the impulse responses in your body. Okay. Do you have any questions? You can take the example of this one. Not an issue. Look into that. Do you have any question? No? Okay.